The objective of the project was to engineer a compliant mechanism that has the ability to demultiply an input by a factor of 20. The first step consisted of filling out the quality function deployment, or QFD, in order to form concepts that are based on the given requirements and the chosen specifications for this project. To optimize the process, first it was necessary to deconstruct the problem in subunits and come up with specific solutions. These then were grouped into 5 concepts. Using the belief map, the choice fell on the symmetric double lever, which can be seen in the center of the presentation. After picking it, the concept needed to be designed, finding K, the length of the parts, and the dimensions of the hinges, and simulated to ensure it worked properly. The hinges needed to be verified as well. The last step consisted of sending the design of the piece to the prom facility in order to be cut, testing it in the laboratory, and elaborating the data that resulted from these tests. Next, we will get into each part of the process with more detail. The QFD is a tool that is used as a preliminary step in order to define specifications that satisfy the customer's requirements. The requirements of the customer, which in this case are the final user and the manufacturer, are objectives that need to be translated into specifications that, differently from the requirements, are measurable and can therefore be used as a reference point for the design. To fulfill the requirement of compactness, specifications about the component size were introduced. For the requirement of high precision, it was necessary to define specifications regarding the deterioration of the piece, like yielding stress of the material. Another important aspect of the QFD is the roof of the house, which represents the positive or negative relationship between the specifications, and therefore potential trade-offs that need to be made during the following step. For example, when incrementing the max input distance, which is a positive change, the deformation becomes less linear, where more linearity is a desired outcome. Based on the QFD, a couple of concepts are formed, which can best adhere to the specifications. These are represented here. Each was considered because it best worked for some specifications. The first concept is the single lever. This was considered because it represents the easiest way to reduce the output. Even if this is the simplest solution, it lacks linearity due to it causing a rotational motion in output and not being symmetrical. The second is the double lever, which is similar to the first option but guarantees more compactness for the same demultiplication. The third option consists of adding a double compound to the second concept. This has the advantage of reducing vibration and maintaining rectilinearity, but adds a layer of complexity to the system, which reduces predictability and makes machining of the part harder. The fourth option is centered around making the displacement as straight as possible by introducing symmetry over the axis of motion. Its parts are still derived from the double lever system. The fifth proposed concept is a symmetric system as well, but with a different layout of the hinges. This, compared to the others, is the most complex system from a predictability standpoint. The following step is the concept selection, which, to make the best choice based on the team's competency, is done for a tool called a belief map. In the map, each requirement is listed in the first column vertically, and each concept is in the first row horizontally. For each concept, it is written down how likely it can satisfy each requirement based on the team's shared knowledge. This guarantees that the final chosen option is the best one based on its characteristics and the understanding that the people designing it have. The result of the belief map was that the best concept is the fourth one. In this section, the steps to define the final design of the selected system are analyzed. The order of these steps is verifying the kinematic chain, simulating the concept using MATLAB, generating the final design of the hinges, and creating the CAD drawing. The first decision was to conduct a kinematic study because, through this, we can size the length of the horizontal levers to achieve a displacement of 1/20th. As this image shows, using Mathematica, it was possible to obtain a demultiplication factor of 0.044 and a maximum deformation of 12.9 for the most stressed hinge. All these calculations help to understand the system so that it is possible to derive the coefficient k and to design the thickness of the hinge. Using MATLAB, the system was recreated with the multibody function as shown in the animation, and the output displacement was verified by applying an input of 10 mm and a force of 1 Newton. To achieve this, it was necessary to define a stiffness factor k, which in our case was set to 1.2 Newton millimeters per degree. By iterating this process and adjusting the length of the rods, a final maximum hinge deformation of 13.9 degrees was obtained. The system showed a maximum deviation of 5.5% from perfectly linear behavior. After simulating and dimensioning the defining length of the mechanism, it was necessary to choose how to design the hinge. The first step is to select the type of hinge, decision that fell on the notch hinge. This type of hinge is defined by the thickness T of the notch and by the length of the socket X, as is shown in the picture. In it, there is also a formula relating the spring torsion coefficient K to the thickness and length of the socket, from where we can isolate the thickness of the hinge. To find T, it is assumed that X has a length of 3 mm. With the values reported here, we obtain a thickness of 0.393 mm. As the final step, the 3D drawing was made to have a visual representation of the piece, and the 2D drawing of the system was made because necessary for the industrial cutting of the component. In this process, particular attention was paid to the constraints required for fitting the piece with the Kelvin clamp. The finished 2D CAD file was sent to the Brown facility, where a plate of C67 steel was cut out to match the project. The type of cutting used were laser cutting for the holes where the wire of the EDM system would be inserted, EDM cutting to define the geometry of the component, and milling for the V-grooves. The operator needed to trace the path of the EDM machine in order to optimize the movement of the wire and the time necessary to finish the piece. After getting the piece from the Brown facility, experiments were done to measure the precision of the component. The obtained data was then elaborated by interpolation in order to get the best fit line and check if the design component has a linear behavior and if the output is effectively 1/20th of the input. During the measurements, some issues arose. First, as is visible in the video, the application point of the force was not aligned with the center point of the input. Second, due to the thickness of the hinges, the rigidity caused the system to be subjected to a higher force than the Kelvin clamp could handle, making it impossible to reach 10 mm of displacement in input. The equipment used in the laboratory consisted of 2 lasers that measured the displacement in input and output thanks to a couple of mirrors, a Kelvin clamp, which is a constraint that blocks all degrees of freedom, and the input system that applies a force on the component. In addition, a sampling frequency of 1 kHz and a modulator to add a sinusoidal signal in input and output to improve reception were used. Using RStudio software and the collected data, a thorough analysis was conducted. Measurements were taken in 2 different ways. The first method involved loading and unloading the mechanism to obtain the hysteresis expected from simulations. In this case, steps appear in the data due to the fact that loading and unloading were not applied continuously. The second method involved measurements taken only during the loading phase, where the steps in the data were intentional, simulating a sampling process by applying an input of 10 to the 5th nanometers at a time. Graphs were then generated to highlight the relationship between input and output for both tests. In the first case, a slight difference between the loading and unloading phases can be observed, likely due to the hysteresis effect. However, this effect is not particularly evident as the applied input is smaller than expected. In the second case, 2 slight shifts are noticeable, caused by measurement inaccuracies at 2.5 times 10 to the 5th nanometers and 3.5 times 10 to the 5th nanometers. In both tests, a linear correlation between input and output is evident, as well as the previously mentioned sinusoidal signal. A linear regression was performed for each scenario, also analyzing the hysteresis effect separately for the ascending and descending phases. Considering the entire hysteresis process, the linear model returns a slope coefficient of 0.04586. Analyzing only the ascending phase, the slope is 0.04549, while for the descending phase it is 0.04592. In the case of the stepwise measurement, the slope coefficient is 0.04586. The residual plots for the various measurements reveal areas with dense clusters of points and others where the data is more spread out. This pattern occurs because, during the loading and unloading phases, the input was not continuous. As a result, in time intervals where the input remained constant, the measurement system sampled the same point repeatedly. Comparing the acquired data with the DL model, which is an expected slope coefficient of 1/20th, the maximum error observed is 3.661% in the ascending phase, 3.323% in the descending phase, and 3.639% in the stepwise measurement. A pattern is noticeable in the residuals, which may indicate underfitting. However, applying a higher degree regression does not change the residuals, suggesting that the reduced input prevents an appreciable hysteresis effect. Additionally, in the residuals of the stepwise measurement, the previous mentioned shifts are also visible. These simulations provided promising results. However, during the data acquisition phase, several inconsistencies emerged between the mechanism and the entire measurement system, compromising the stability of the component. In several tests, in fact, the system came out of the Kelvin clamp. This issue occurred frequently because the force applied to deform the flexure hinges exceeded the spring's retention capacity. The main cause was the excessive thickness of the hinges, which required a deformation force greater than what the spring could counteract. Another problem was the thickness of the plate, which was 5 mm, the same as the height of the laser used to detect the output. This configuration prevented the mirror from reflecting optimally, compromising the precision of the measurement. Furthermore, it was not possible to apply the displacement exactly at the intended central point, causing additional inaccuracies in the system's deformation. Despite these difficulties, and given the reduced displacement and input, the obtained model exhibited behavior approximately in line with the predictions.